Thank you for returning for part 2 of lecture number 22 by Dr. Emanuel. Right now we're looking at Cartesian and spherical coordinates, how they're important and how we have to look at them. We have two different angles here. We have theta and we have phi. We have phi which is related to the z component, as we're able to look at phi here. Phi for the angle, and as we have rho, this rho here, if you take the right angle, okay, this is at a right angle, this is parallel with the XY plane, as you can see, so this would be 90 degrees. And so we have the z component is equal to rho times what? The cosine of phi. So this here is our height. And what is parallel here? We have our sine of phi is equal to what is paralleled with our XY arc, and which is the radius. Then when we come down here and we look at theta, as P is projected onto Q, as this point is projected onto the XY plane, we're able to have the cosine r times the cosine of theta equal to our y component, and to our x component, and our y component is our r times our sine. Opposite over. So here is something we need to just keep in mind whenever we're working with the spherical and Cartesian coordinates. We need to be able to find out how we'll be able to convert our x, y, and z's at any point in the curve, in the sphere, and convert them to rho, theta, and phi. And we just used, as we just saw, trigonometry. That's all we used. In the blue, we explained how we used the blue and how a z is designed. The leg of z is our rho times our cosine of theta. That's the length. Then we found out also that on the other leg, on the right leg, we found out that that's phi times the sine of theta, which is also equal to r, which is the radius in the x, y plane. So it's only 4 minutes, so let's do an example. We'll do part of an example. Okay, first we want to find the centroid of a uniform spherical coin bound by z squared equals x squared plus y squared. This is the boundary for the cone. The equation for the cone and equation for the sphere. X squared plus y squared plus z squared equals 4. And we know that x squared plus y squared plus z equals r squared. So, in our first step, we need to be finding what is r, what is theta, and what is phi. So, using this equation, we're able to come up with that r is equal to 2. Because r squared, which is 4, square root of 4 is 2. So, also for phi, You see that phi makes a what? 360 degrees, so it's 2 pi. And what about for the cone? We see here that this is for 45 degrees. And as you take this 45-degree angle that you have here, from the z over, it's only 45 degrees, then it will go 360 degrees around. Now, if we don't have a curve, how do we determine this? Just using numeric numbers. So, the first thing we would do is we like to find the spherical cone boundaries for x squared plus y squared equals z squared. So we're going to plug in for x, r, times the sine of theta times the cosine of phi. We're going to square it. We'll plug in for y, r times the sine of theta times the sine of phi. We're going to square it. And for z, we're going to plug in r times the cosine of theta and square it. Once we're able to do that, we can pull out an r squared and a sine squared of theta out of each one on the left-hand side of the equation. Then we only left with cosine squared of phi plus the sine squared of phi, which is equal to 1. And now we can divide, bring cosine to this side of the equation, and we get the r squares to cancel out. We just get sine squared of theta over cosine squared of theta equals tangent squared of theta, which equals 1. And so we find out at 45 degrees, or at pi over 4, that's what we have. And so now this correlates with what? Yes, lo and behold. It correlates for what we see graphically. Excellent. Okay, so we still need to find the volume. Okay, so let's come back to do the volume. Right now you saw how we did the boundary condition for the cone. Remember that, because we'll have to do that in every problem that we solve. Thank you.